Okay, hello everyone. Hope you're all doing well. This is I'm Matthew Bonner. Some of you may know me before. I'm the current treasurer of the SFP London Student Chapter. We're so pleased to have so many of you here today for what's looking to be a great talk. Today we've got a really unique speaker, Dr. Wojciech Węgrzyński, who's the deputy head of fire research at ITB, which is the Building Research Institute at Poland. Wojciech straddles a really unique line in fire research. He sort of straddles that point between industry and research, which means, as well as being the author of over 20 published research papers in lots of really impressive journals, he's also seen a lot of fire, and I mean a lot of fire. Like I'm very impressed at the number of fires he's seen, and that can give him a really unique insight, which I'm hoping he'll share today. Today he will be talking about the coupling of wind and fire dynamics, particularly for modelling. So thank you so much for talking for us, Wojciech, and let me hand over to you, Matt.
Thank you a lot, Matt. It's a great pleasure to be in here with you, and I'm, as someone involved in SFP in my own country, and I'm really impressed by the performance of the Great London Student Chapter, the 100th chapter of the SFP, and yeah, I'm very happy to be here with you. I guess I should now take over the screen.
Oh, can I add quickly as well?
Yeah, go on.
Can I just add that the Q&A is open throughout the talk. So if any questions come up during the talk that you would like to ask, just post in the Q&A and we can see it, and we'll get to that at the end. We'll select some for Wojciech to answer. Sorry, thank you, Wojciech.
Yeah, that's cool. I've shared the screen. Can you see the slides?
Yep.
Okay, that's great. So once again, welcome to everybody in here with us today. My name is Wojciech, and I'm really happy to take you through the journey through wind and fire. Let me introduce myself properly. My formal background is fire safety engineering. I did masters at the Main School of Fire Service in Warsaw. That was a few years ago. And I have done my PhD in civil engineering at the Building Research Institute of Poland, where I work. With my background being fire safety engineering and civil engineering, it gives me a little biased view over the wind and fire and interaction, because the scope of wind and fire is vast, and it includes also wildfires, forest fires, all kinds of fires, and for this phenomena, wind is as important as to fire safety engineering. But due to my background, I will focus my talk on building fires, because that's the key part of my expertise. But hopefully, if any listeners are interested in the fire dynamics and the wind in different settings, I hope this talk will still be quite useful to you. I'm with ITB since 2010, and currently I hold the deputy head of fire research department. I am also involved in the Polish SFP chapter, as mentioned, and yeah, my research areas are CFD in fire safety engineering, smoke control, visibility in smoke, and recently traveling facade fires. That's enough about me. In the talk, I will try to answer 3 questions related to wind and fire coupled modeling. First of them is, why would we like to model wind and fire at the same time? Second question would be, what do we want to model when we do that? And the third would be to help you in how actually we can do that. I hope these 3 questions will be answered sufficiently to your satisfaction. To start off with a punchline, why Wind is definitely one of factors that can drive the fire dynamics, and they can absolutely change an outcome of a fire in a building or whatever setting it is. Wind, as you can see in the picture above, it was taken yesterday. The reason why this plume of a flashover fire is horizontal to the surface of the ground is because of a wind. Wind is such a strong force, it can completely change the fire dynamics and smoke dynamics in the building, and in consequence change how the safety features, safety systems of the building will work in a fire. To put numbers to that claim, in a report by Fire Protection Research Foundation and NIST, where they looked into high-rise building fires in which there were casualties. Out of 565 investigated fires, 60% of them may have had an impact of wind in it. It's number of fires for which they did not exclude the impact of the wind. For 30 of these fires, which is 5% of all, the wind had confirmed impact. It means that wind has definitely been one of the major causes of the loss of life in that case. And for 10%, this was determined as probable. So 15% of investigated fires in which there was a loss of life had been certainly impacted by wind, and most of them were most likely impacted by wind. So we are talking about not an exotic phenomena. We're talking about something that that accompanies many of fires in built environment. Wind acting on a building in which there is a fire will change the phenomena happening in there, and usually this change will be for the worse, unluckily. With wind, the fire will spread quicker, the smoke will move further, and as wind being a transient phenomena, a change of wind direction may often cause a change of the smoke dynamics in the building, which is unfortunately one of the causes of loss of life in fire, especially for fire safety officers. If we try to break it up, we can consider wind as exogenous driving force for the fire dynamics, a force acting from the outside. While on the opposite, the fire, the buoyancy and the phenomena that accompany the fires can be considered endogenous forces, the ones that act from inside. So in the end, the outcome of the fire will be strongly related to the balance between these forces, and a claim that I can make quite with large, I'm quite sure this like this, it's that an outcome of a building fire with and without wind will be completely different outcomes. What's really interesting about wind and fire is this love between them goes both ways. It's not only wind that changes the fires, it's also fires that can cause a wind on their own. And this is one of the most terrible phenomena that we can encounter in fire science. These firestorms or fire wheels caused by huge thermal plumes are said to have a force comparable to a hurricane wind, and you can see that on post-fire investigations after huge mega fires that occur on the planet. On the picture, you have a fire that happened on this day 28 years ago in Poland, in Kuźnia-Raciborska. It was one of the biggest wildfires in Poland, and it caused a loss of lives by 2 firefighters. And it was claimed that the wind on it, the fire on itself created such a strong wind that it actually destroyed the forest. The trees on the picture are not burned down; they're ripped away from the ground by the force of the wind that was caused by the fire. From the reports of that fire, the reports claim that the wind velocity was up to 30-40 meters per second, which is enormous. So yeah, in fact, the fire on wind can form a truly horrible combination of forces very, very devastating. As we are aware that wind and fire go together, and we must include wind in our analysis. For my own practice, where do I use this? I try to use this way of modeling, this introduction of wind into my numerical analysis for analysis of the interior of buildings, as what's happening inside of the buildings, and estimation of asset criteria to determine whether the building is safe or not. This is something that we sometimes do, that wind is included in this analysis. We definitely want to use wind when we analyze the exterior of the building and the consequences of a fire to the outside. And here I stated that it's for near field, because we use CFD for the nearby surroundings of the building, while if you would like to investigate, for example, regional smoke spread, you probably would be better with CMAQ or other models that are better fit to do that. And the third one is we definitely use wind and fire coupled modeling to investigate venting, and especially natural ventilation. And this is something that is profoundly connected with wind. If you have a building with natural ventilation, the outcome of a fire with a wind will be absolutely different than outcome of a fire with no wind conditions. In fact, with the different wind angle or different wind velocity, you will end up with absolutely different outcomes as well. And what makes this even worse is that there is no easy way to say which wind will be the worst, or which wind velocity will be worse, because different boundary conditions of wind will lead to completely different outcomes. So that's quite a challenging aspect, and we really focus on researching this topic in ITB to try and understand what kind of wind would be really damaging for the performance of natural ventilation system, and how can we simplify this process of design, that we can say we include wind, and that we do it good, and it doesn't require thousands of simulations. If you go deeper into the natural ventilation, it's not only that with different wind you will receive different performance of the system. It's also each part of the system, each device of your system will act differently under wind load, which means that our paradigm of natural ventilation, that we tend to estimate the aerodynamic free area of the natural vent and put that into calculations and have a total area of vents on our building and be happy with it. It's actually quite untrue, because your vents, each of them, will have a completely different performance depending on the conditions inside and outside of the building. And definitely, when you have wind or you not have wind, you will have completely different outcomes on your vents. So in the end, if you really want to investigate the performance of your natural ventilation system in a building, you must include wind in your calculations. Without that, you will not reach an image of the system as it will work in reality. But yeah, it's not only negative. As we tend to understand wind better and better every year, we also try to use that knowledge of the wind building interaction to try and improve the characteristics of the ventilation systems. And I would say we're rather successful with that, because as we have found, if you place certain aerodynamic shielding elements on the roof of your building, you might actually produce quite positive conditions for the natural vent to operate in wind conditions, to the extent where performance of a vent in wind is better than without wind. So we're actually using wind to assist us in smoke venting rather than destroy the ventilation performance. And this is certainly a new area of research that we are pursuing. But from the first studies we've published, it's very interesting, intriguing, and hopefully will help us design better systems in future. Obviously, wind and fire. To investigate wind, we are focusing on simulations, but it is obvious that wind engineering is born in wind tunnels. Wind tunnels are to wind engineering the same thing as calorimeters for fire, and this is the main tool to investigate this phenomena. And thanks to our determination and our long-lasting efforts to get this, we finally got it. We got our own wind tunnel in ITB, which was delivered just a month ago to us, and we could not be happier about it. It will open a whole new era of wind and fire research. It's a wind tunnel that is placed within the fire research department, so it is absolutely focused on this aspect of research, and we really hope to put it into great use in the nearby future to produce high-level science on wind and fire interaction. I've also heard that the pictures do not really give the scale well of the tunnel, so here's one with me next to it. It's at the inlet. It's a proper wind tunnel, and the fans on the right are all are 2 meter diameter, so we can really do some large-scale fire and wind research in it. And yeah, that's the final testimony to why should we model wind. We are so convinced that wind must be involved in fire analysis, that wind is such an important factor that we have built this facility to investigate it. We are absolutely certain that wind must be a part of fire analysis, otherwise the fire analysis are not really true. To move on, so let's say we have a common agreement that we would like to investigate wind in fire safety engineering. So yeah, but what is that we want to investigate? What is wind? And surprisingly, it's not that easy to find proper wind engineering in the fire science. In many of the research, wind is used as a general term for movement of air, in which any forced movement of air against the fire is said to be a wind effect. That's especially true for combustion science. At the same time, it's true and untrue, because yeah, you can definitely call this movement wind, but wind is way more complex than just velocity of air opposing on a flame or an item that's burning. Wind in civil engineering is a complex pressure field or force acting on your building that changes in time and space. It's a complex phenomenon, and simplifying wind effect into just airflow velocity is like simplifying fire into a standardized temperature curve. It's taking all the dynamics from it and just turns it into a number that may be useful for a test or to check the small scale parameter, small scale phenomenon. But this is not really what wind is. Wind is very complex, and if you start going into proper large scale and try to investigate the wind effects on a larger domain, you start noticing that these effects may be truly complex and fascinating, and they will, depending on the location of your building against the flow of air, depending on the building surroundings, depending on the wind boundary condition, you will end up with completely different results. And yeah, for me, understanding these effects, this complexity is what really wind and fire engineering is. Wind is difficult to describe because if you take a look at wind at different heights, for example, you will end up with completely different flow patterns and flow velocities. You may also end up with completely different wind directions even. That's absolutely natural. And yeah, wind at mesoscale is a really complex phenomenon. Fortunately, our buildings are in the lowest part of the troposphere. Well, some of them try to escape that part of troposphere by reaching extreme heights, but most of the buildings we design are in the lowest part of the atmospheric boundary layer, so that simplifies it a bit. Yeah, let's talk about scales. If you take a look at the wind phenomena, there's so many different phenomena happening at different scales. Professor Schlunzen has prepared this beautiful graph that illustrates the range of scales of atmospheric phenomena happening that are somehow connected to wind, from tiny turbulences up to minuscule scales to global circulation, which you would consider the whole planet as your model. Obviously, for fire engineering, we're not interested in such a vast range of scales. If you try to use the same notion for fire, I've tried to put fire phenomena in the same scale, and it became evident that building fires, wildfires, and let's say the smaller fire-related phenomena are within the atmospheric microscale, the lowest part of the troposphere and HBL atmospheric boundary layer. So yeah, this phenomena seem to be possible to model them along with wind, because this type of microscale phenomenon are usually considered for urban comfort and urban flows. So these phenomena are investigated by wind engineers. With regard to the smaller phenomena, we usually handle them with models. We don't really model turbulent combustion up to the smallest scales. We tend to put them as models into our simulations, and the same can be done with wind and the phenomena that are of larger scale than fire safety engineering is interested in. More complex, larger phenomena must be simplified and supplied into our CFD, so we don't have to solve for them. So yeah, there is this scale somewhere in the atmospheric boundary layer, which we would call a microscale. It may be funny, but it is called like that, in which it's feasible to perform coupled wind and fire simulations. Now, if you have your wind boundary conditions, your ABL model, and you want to put it into effect, you have to consider angular sensitivity of the analysis, because the direction of the wind will change everything in your simulation. Here are two examples of wind acting on a small warehouse building in the middle of the view from two different directions. And on the right side, you can see the pressure patterns on the buildings, which are completely opposite of each other. On one of the images, the inlets are in under pressure and outlets are in over pressure, and it's reversed in the other one, causing two completely different ways how air will flow inside of the building, because the direction and the airflow velocity inside will be completely different. This means that you have to be careful not only about the transient characteristic of wind and the fact it changes with space, but you have to also take into consideration the direction of the wind action. Now, if we agree that we want to model wind and we want to make it properly, we want to make angular sensitivity study, etc., there's one tiny detail to be figured out. What wind velocity would we like to use for our analysis? And boy, that's another problem, because there is no universal answer to that question. In structural engineering, you would probably work with something like fundamental basic wind velocity for your design, which is a boundary condition that with good certainty will, if your building can sustain this load, it's more or less safe. That's how you would simplify this. However, if you want to put 20 meters per second velocity and investigate fire in the building, or even worse, investigate systems of the building with such a powerful force, I highly doubt you will get any meaningful results out of this analysis, because this wind velocity will be absolutely extreme for the fire phenomena. So yeah, maybe we should move into some form of statistics and working out the wind rows and finding out probable wind scenarios. That's actually quite an interesting approach, and we are currently investigating the feasibility of using this approach into that. We've submitted a quite large grant application to really go deep into combining wind and fire and risk together, to figure out what are the reasonable wind forces on fires and what kind of wind to include and what not. However, at this point, I would think this to include the wind rows, the statistics of wind in your simulations would be rather difficult, because it's quite difficult to get the good data on that. If your building is next to an airport, you probably have great data, but if it's in the middle of a city like London, you probably have a difficult time obtaining very good wind data for this particular location. For the city at whole, you will get the data, but for location, no. And yeah, to solve for that location, you would have to model excessive part of the city to actually get your boundary condition. So yeah, it is difficult. Sometimes we want to use this wind engineering not only for design. Sometimes we want to investigate what happens. This is especially true if you're a fire scientist and you have performed an open air fire experiment and you would like to rule out the uncertainty of wind on your fire experiment. We usually resort to on-site measurements and historical data in such analysis. We usually have this nice meteorological station next to our experiment, and yeah, it measures wind as the experiment goes. And then you would like to model that. And this also gives quite a trouble, because you cannot just take the wind speed of your anemometer and put it into simulation as a boundary condition, because the thing you have measured, this is not wind, it's the effect of wind in this particular point of space where your device was placed. And if the device was placed elsewhere, you would most likely receive a different measurement. So instead of using this data as a boundary, you must take a step back and probably figure out what kind of wind profile would create such a result in this point of space, and then use this wind profile for your simulation. If you're investigating an experiment you have performed, then this is doable, because you can eventually find out the correct wind profile that corresponds to the conditions you had. It's slightly more difficult if you want to have that immediately, as you are on the field and you need to model how the wind will affect your fire now. In this case, you have to use some really sophisticated methods to reverse engineer that, and these are called mesoscale microscale coupling models. Example of that model is, for example, Wind Ninja, which allows you to take measurements and turn them into boundary conditions almost on the fly. But yeah, this is still something very young, and hopefully we'll get really good models in the future. And if we get that, then we'll be able to immediately turn measurements into boundary conditions of our simulations and perform the simulations immediately. That can open a whole new array of possibilities for wind and fire coupled modeling. So yeah, how we deal with this uncertainty. In our engineering cases, we usually tend to do wind sensitivity study for different angles, like on the drawing on the left. We usually use either mean wind velocity for the area or some sort of fractal of wind velocity for the area. It depends on the arrangements with the client. And it's not perfect, but it seems to be good enough at this moment for practical fire and wind engineering. To run such an analysis with wind and fire for all of these discrete wind angles, it would be very expensive. So we also have developed a decoupled method in which we investigate the wind separately and first try to find the most onerous wind conditions that are most likely to create troublesome effects inside or outside the building. And then for this particular angles, we performed coupled transient wind and fire CD analysis. So yeah, the wind analysis are performed as steady state. They just give an image of pressure on your building, and these simulations can be performed fairly quickly compared to the transient wind and fire coupled simulations. And this is how we can actually use this commercially, because otherwise, if we had to do all of them for a commercial project, that would be very, very expensive. I'm like 25 minutes into talk, and this is probably the first practical advice given. I hope I can improve in the last part, though. So yeah, this is an example of the results of wind effect at different angles, and it shows you the smoke plume of the fire. Image on the left is like almost a perfect Gaussian plume that you would receive with a Gaussian model, and it's how you would calculate with a hand with a calculator on paper. And the image on the right, which is not that far off, it's just 30 degrees to the left with the wind. It gives a vastly different image of a smoke plume spanning over large chunk of the part of the city that we simulated, showing you how vastly different the wind effects can be if you start to investigate them with a fire. Okay, so let's get to the practical part. How do we do that? The answer is simple: with computers. And well, to this terrible joke, there's actually some interesting story behind. Because 100 years ago lived a man, a genius called Louis Fry Richardson, and he had a dream that then the dream is illustrated here, that this is 1920s. If you could connect scientists from the world who would measure pressure gradients, temperature, velocities in the area where they are located, and they could transmit this data to one single place, which he called a weather forecast factory. These scientists could be put in a dome, and they could just exchange the data with their neighbors to create an array of a map of pressure gradients, and this could be used to solve for how the flows will form around the globe and how the weather will change. And these people were calculating the gradients. They were actually called the computers, and surprisingly, this is pretty much how the CFD works nowadays. It's just we use electric computers that calculate this for us. We don't have to build a building with people in it. From what I've read, he lived to a moment where actually computers were used to solve some sort of this, and and he was very happy about the fact that his idea, the technology eventually reached the level when his idea was feasible, and this is the backbone of numerical weather prediction. It was also quite a bold move to propose such a solution, because a few hundred years ago in England, weather forecast was punishable by death. So I would not rather try to do that. Yeah, hopefully you don't need thousands of people to do that today. You just need a computer with some solid computational capacities, and you can quite successfully perform wind and fire coupled analysis. And obviously, I'm not able to give you the whole image on how to do it from start to the end, but I hopefully can give you some good advice that will significantly improve your capability of modeling wind and fire. Would be to resort to the computational wind engineering best practice guidelines. There is a field of science called computational wind engineering, which is probably 10 times bigger than the fire science. And these people, their goal is to model wind with computers. And one thing they do really great is they share the best practice guidelines on how to do this properly among each other. They publish them, and there's unbelievable amount of resources available on how to perform good wind engineering analysis, computational wind engineering. I would definitely start with Professor Blokken's 50 years of computational wind engineering, which summarizes the history, the developments, and the best practice guidelines that were introduced as the years moved. And this paper has absolutely astounding amount of practical knowledge in it related to how to perform engineering analysis in general, but computational wind engineering in particular. One thing about the paper, he actually in the appendix, he identifies which kinds of review papers were written about wind engineering, and he said that there was at the point of writing the paper, there was no review on fire and wind. And yeah, we saw our chance in there, and yeah, 3 years later we've published this, which is our review of wind and fire coupled modeling best practice guidelines. It's a two-part review paper in fire technology. We even received a best paper award for that work. So I hope it's really useful. And this paper contains a summary of the best developments in wind and fire coupled modeling. So if you're interested in that, I highly recommend you start with our paper and Professor Blokken's 50 years of CVE, and this will significantly improve your ability to model wind and fire. My tip number 2, understand your computational domain. This is something that distinguishes wind and fire engineering. We tend to build domains quite differently. In fire engineering, we usually tend to model the interior of the building with the outlets, which are our ventilators or inlets to the building, being modeled as pressure planes. That's very simple and very efficient, but as you will see, not really fit for wind engineering. I also see a lot of simulations, a lot of research where wind is introduced through a very small external domains, where you would pop some kind of velocity inlet boundary condition on one side and yeah, put some air movement into that domain. And the third approach would be like the computational wind engineering way, as explained in our fire technology paper. If you take that into details, if you model outlets as pressure planes, so you just end up your domain at your inlets and outlets, you probably will get quite false pressure distribution on through your building. This is connected to way how inlets are modeled, how gauge pressure is modeled on inlets, and it's very difficult to get this correctly that yields meaningful results. The image you can see on the right, the sports arena, which we modeled it like this, was possible only because we had forced mechanical ventilation to supply air into the arena. So we were quite sure what kind of pressure gradient we have in the building, and this was the only way we could solve that. If we didn't have that, this way would not be feasible for this project. If you build a small external domain, that is slightly better because you can certainly resolve the flow through the inlets and outlets better. But you really cannot say you can model wind with such a setting. This is because you will artificially change the wind as it moves around your building. You will see flow acceleration if your model is not high enough. You will also see some incorrect stuff happening behind your building, which has huge effect on the overall flow in the domain. So by doing that, it will look like you have solved wind in your simulation, but it will not be a solution for wind. The only projects in which this approach may be somehow feasible would be ones in which your building is located within an urban canyon. So it is limited to a certain area of your city, and you are fairly certain that there will be one or two dominant wind directions in this canyon. And in these cases, this might be feasible, but in most cases, no. So the correct way would be to build a really large domain that conforms to the best practices of computational wind engineering. And this is when you start really solving for wind in your analysis. This is the stage at which you can say the wind was included as a factor, as a physical phenomenon in your analysis. It requires quite a large domain and quite a lot of details in it, because wind is a phenomena taking place on a larger scale than fire. So to solve for that, you need to include more obstacles in your simulation than you would do if you only were solving for fire. From the best practices, we have some rough guidelines that the size of the domain that would allow you to reasonably model wind. And I understand that this is something that puts people away from the wind engineering and fire engineering as a coupled approach, because these domains are really huge and they seem very costly. But in fact, it's not actually completely true, because mesh is your friend in here. And while for fire phenomena, we need really fine mesh to capture the entrainment of air into smoke plumes and capture all the effects associated with the smoke movement in your building, in wind engineering, the meshes we are using are much coarser than we would do in fire safety engineering. And this is why we can use mesh functions to grow the mesh in our domain. So the further we are from the building in which we are solving the fire, the coarser mesh we can use. If you use unstructured meshes as us, we use tetrahedral meshes or polyhedral meshes in our analysis. We found a sweet spot at 1.3 factor, so each cell element moving away from the building is 1.3 of the size of the previous element. So this way the mesh grows as we move away into very large dimensions. So in the end we receive elements with like 5-meter diameter, which is sufficient to solve wind at high altitude. You don't need 10-centimeter mesh to solve wind at high altitude. So we can expand the domain vastly, but really not put that many additional elements into the domain. So it doesn't really cost that much to build the domain, and the improvements you get in the solution are enormous. If you use FDS and structured meshes, you just need to maintain 2-to-1 ratio, and you don't want to make meshes that have just one layer of elements. But you can use pretty much the same principle to build your mesh outside of your model and significantly increase the size, the dimension of cells in your domain to have very coarse mesh that spans over a large area. And because you can assign meshes to certain MPI processes, to certain processors in your FDS simulation, you can do that very efficiently nowadays. On the other end of the scale, there are fine details that might affect your flows in the buildings or in the ventilators. That's pretty much the place where you get the finest details, are the vents. And the question is how detailed the vents have to be to solve for wind. The answer is they do not really have to be that detailed. These are examples of very fine engineering we have done to estimate the effects of small elements of the vent on the flow rate. And you can see that the changes of the flow rate are like 0.02, 0.03 in terms of the flow coefficient, while, for example, placing an aerodynamic aerodynamic element in front of the ventilator will change it by a factor of 1. So these are very tiny changes in the performance of the vent. Most likely do not need to be put in your analysis unless you are really doing really fine engineering. So in the end, you don't have to go that detailed in your inlets as long as you do the rough geometry of the opening and the rough geometry of the walls of the way how the inlet opens. If you do that correctly, you don't need to go that deep. The fourth tip is how to put the wind in your simulation, because this is not easy. As I mentioned before, you cannot just take wind velocity and pop it on your boundary condition and pretend this is wind as we use it in wind engineering. You need to put something called wind profile into your simulation as your boundary condition, and this wind profile will change the wind velocity with the altitude. It may change the wind velocity with time. It may change the wind direction with time. And very importantly, it will provide certain turbulence characteristics into the simulations that are connected with the roughness of the area in which the building is placed. Because depending on where your building is placed, if it's placed in the middle of a desert, if it's placed in a forest or in a dense urban development, you will have three different winds in there and three different roughness characteristics. So your wind profile must include for that. If you use K-epsilon modeling, RANS modeling for wind, this is fairly easy because you have these wind profiles described in literature that determine the wind velocity and K and epsilon parameters as a function of altitude, which allows you to fairly easily incorporate these profiles in your simulation as a boundary condition. If you are using LES modeling, because LES is a transient solution, it's not averaged over time, it's averaged over space. You must take additional precautions because your wind, to have this effect of turbulence, the wind changing with the time of in your simulations, you must either provide a transient inlet condition into your model, something that we call synthetic turbulence generation, boundary that mimics the way how wind acts in reality, how it changes its velocity. Or you can build a large domain which is filled with elements that correspond to your terrain roughness. So you supply a constant airflow at your inlet, and once the wind passes through this array of obstacles and reaches your building, you eventually end up with a profile that you expected. This is tedious, but can be done, and a comment I can give you is that it must be measured at the building of your interest. It must be measured, and this is the only way you are sure that the wind boundary condition you supplied has the turbulence characteristics you have expected, and this will have a huge impact on your outcomes. Finally, decoupling the analysis, how to make it cheaper. As I mentioned, we try to do the initial assessment as steady state and just investigate the pressure on the buildings. This is an example of a building being rotated and different pressures being estimated on it. What you are looking for are the overpressure and underpressure on your inlets, the openings, the smoke ventilators, doors, and other sources of air that is incoming to the building. And you would like to seek for the cases in which the difference between the two is the greatest, the ones in which you have the biggest difference between inlet and outlet, or the cases in which you have extreme values at your inlets and outlets. So a case where I would have the highest overpressure on my inlets, the lowest pressure on my inlets, this would be the cases that I could expect the wind effect inside the building being the strongest. And once I identify these cases, my flow chart of my work would look like this. I would first seek the worst case wind scenario, and once I found it, I would use that wind scenario in my transient wind and fire analysis. The other way, brute forcing it, simulating all of the fires in a building with wind, with different wind angles, it's possible. It just costs much more because the transient simulations of wind and fire are taking a lot longer than steady state simulations of just wind, because you obviously have to solve for a longer duration. So yeah, this is a way how we can make this a feasible engineering and not just a scientific endeavor. So yeah, that's the 5 tips, and let's wrap it up. This is, by the way, the interior of the building that I was showing through the presentation, the one with the triangular part of the city being modeled. And yeah, we've done wind engineering for that one, and it worked out really well. So we're really happy with this building. I've tried to help you find answers to why would we model wind, what would we be modeling, and how would we do it. And hopefully in all of these areas I've provided you some knowledge regarding that, and you can take more informed choices in your engineering path. We are aware there's a lot of gaps in knowledge. This is not something being routinely done, and we understand that it is something new to fire engineering to introduce high quality wind engineering in it. We definitely lack experiments that would include both wind and fire. This is something that's very difficult, because if you are performing large-scale fire experiment, you usually have to take wind as it is. You are not able to change wind during your experiment. I think the only facility that can do that is IBHS in USA, where they actually can do that. But if you're not IBHS, you are not able to craft the wind for your like in your fire experiments. And if you want to do that and you have a wind tunnel, you're not really able to model fire in it, because the difference of scales and the fact you're not able to maintain Freud and Reynolds similarity at the same time really prevents us from doing fine wind and fire engineering in wind tunnels. This is something we have to work around with using CFD and validating our CFD with wind tunnel, and this is the route we are taking. Furthermore, not all best practices from CVE may be applicable for fire safety engineering, because there are a lot of things that we consider different in fire safety engineering. And for this, I have a chapter in the paper in fire technology, which I would like to refer you to, and you can find more answers on that in there. We don't really know how to judge the results of our analysis regarding to the exterior of the buildings, because we don't have tenability criteria for external domains outside of the buildings. We are so focused on the interior of the buildings, we can very easily say, okay, my visibility breached the criterion, so my building is safe or not safe. But we don't have such criteria for exterior, and this is a problem that we find analyzing smoke spread in urban environment quite difficult, because some people would say they don't want any smoke in their building from a fire of let's say a metro station 5 blocks away. Others might say they want some as low as reasonably possible values. We don't have an answer which one to use. And yeah, finally, introducing the wind into modeling, especially if you want to use on-site measurements or historical measurements, is proving to be challenging, and we would like to work on that aspect to streamline the process and make it easier to use in practice. And yeah, we have published some papers on the topics mentioned in this talk, and if you would like to get some more details on how wind and fire is performed by us and how we use it in various aspects of fire engineering, I would kindly refer you to these studies. So yeah, that concludes the talk. Thank you very much, and I'm happy to answer any questions you have.
Okay, thank you, Wojciech. That's really good. Yeah, have you put stuff over? So, yeah, so we have thank you very much for the talk, Wojciech. It was really good. Very interesting, and we've received quite a lot of questions on it, and keeping in theme with the broad range of topics, with the broadness of the topic, we've got the questions are quite broad in what they're asking. So I think I'm going to start with some of the more sort of in-depth, detailed questions that people are asking, specifically about the presentation, small bits of that, okay. And then we'll sort of broaden out with more general questions about the topic. So there was a question here, just a technical question from Sam Lee. I've published it out here. It was asking about, there was a graph of mass flow with wind angle, and he was just asking, how did you measure the mass flow? This was very early on in your presentation, but like.
If you simulate, if it's in a simulation, you release smoke in your model with a known amount, and it's transported through your domain, and your CFD solver is solving for that exactly. So you can tap into raw data of your solver and just plot the mass of a smoke within a certain point of your model by just asking a certain question to your model. The common way we do that is we present visibility in smoke parameter rather than mass density of smoke, which is essentially the same thing, just presented in a different way. So yeah, it's a way how you tap into data, and any solver you use can definitely present mass density of smoke as an output variable in your model, because the solver is explicitly solving for that when solving the transport equation and the conservation of species in your simulation.
Interesting. That's yeah, I have to say, not delved into the world of CFD, but that sounds cool. Yeah. Sounds interesting. This one, we've also got another question here on some technical stuff, just asking about, with your wind tunnel you showed, which looked amazing, is it possible to measure heat release rate within the wind tunnel, or more generally, is it just possible to measure heat release rate when you've got wind present as well?
This is a very new wind tunnel, and we are not allowed to burn it down yet. So I wouldn't really want to directly measure heat release rate in it, because that would mean we have burned it down, which is very unlucky for the tunnel, clearly. In terms of heat release rate, what you want to measure is the oxygen concentration you have. So as long as you are able to measure oxygen concentration and capture the flow, in terms of, if you can quantify the amount of air that you are putting through your measurement system, and if you can quantify the oxygen, you can get the heat release rate, because the airflow into the tunnel is a fixed inlet and there's a fixed outlet. So if you have oxygen and the flow, you have the heat release rate. It's possible to do mass loss rate measurements in the wind tunnel, but that would be very difficult because of aerodynamic forces that could fiddle with the way you measure mass in the tunnel. So mass loss rate is potentially possible, but more difficult. And the third way, through measuring heat fluxes like radiation heat flux, you could possibly give some estimate on the heat release in a tunnel. So yeah, I can see some ways to measure heat release rate in a wind tunnel, but I really don't want to burn it down. And in fact, if I was to do today, if I wanted to do today some sort of fire experiment in my wind tunnel, I would rather use helium gas to simulate the change of air density in the tunnel, and use that to replicate the smoke plumes, because a smoke plume is essentially air with different density, which has buoyancy. That's what smoke is in terms of smoke analysis. So you don't need the heat part in it to simulate the movement and entrainment. It's nice because it makes it more real, but if you're only interested in the smoke movement, that is not necessary to do that. Yeah.
Okay, that's interesting. I hadn't heard of the helium thing before. That's quite cool. There's also a question here from Faraz Hedayati, who's asking about if there's any research on the effects of gust structure on fire dynamics, rather than just considering sort of mean wind value at all. So,
yeah, that is extremely challenging because simulating mean values is already a hassle, and gusts would definitely be very difficult to grasp. And I would say it would be at the same time very important to be able to represent gust structure, because gusts will be the reason behind quick change of fire dynamics in the compartment. I mean, if you have a steady wind on your building and suddenly you have a gust that not only changes the velocity rapidly, but also changes the direction of the wind, you might have a short-term change of the dynamics inside. And this is one of the leading causes of firefighters' deaths in fires. So in fact, it is very important phenomena to take. If you are modeling with LES, you are probably able to quite straightforwardly introduce gusts into your synthetic turbulence generator. You can just put that within your boundary condition that at some point you have a certain gust. And if you know the gust structure of your input wind, you can model that. With K epsilon, you can play with turbulence intensity, but I'm not sure if you will receive the same quality of results. Probably not. Probably LES would be your best choice to use in this case. And that means that the simulation will be quite expensive and long, but this is possible to do that. Yeah, it's challenging, but important and possible. So you would have to first model gusts, and if you know how to model gusts in your wind engineering, well, then you have to just put fire in there and model them concurrently. The scales are the same, the time scale is the same, so there's a good chance you can just do that. Yeah.
Okay, cool. This actually just came in as well, but it's on the topic of more of the sort of specifics of your presentation. Was someone was asking, is this a closed or open system wind tunnel, the one that you built?
That's a hybrid. It is the air is returning to the inlet through the building. So in a way, it's both at the same time, and due to the way how we structured the inlet inside, we receive fairly good wind profile inside. We're still measuring that. We are still doing improvements in that because we want to install some vanes inside to give us a better control over the boundary condition. We can also alter the rotational speed of the fans independently, so we can. Each fan can be set on different velocity. Actually, I do that with my smartphone. That's welcome to the 21st century. So we can receive as good field inside the tunnel as we would have in a closed system. but we also have some benefits of having it as an open system, because we can reverse the tunnel, and then the large inlet I shown on the picture is an outlet, and I can put much bigger structures in front of that and have some sort of wall of wind model. That's a different way how to model a wind in wind tunnels. It's more close to what IBHS is doing, and this potentially will help us do some different results. And in future, we want to build another segments of the tunnel to make it longer, to give our more control over the boundary condition. But yeah, answer if it's open or closed is not an easy one. It's some sort of a hybrid.
Okay, interesting. So actually, we have two people who've asked. I realise we're now sort of been slightly over time for the hour we put aside. So let us know if you have to go anywhere. But there's a lot of questions, so it's good to go through. We've actually got two questions which are kind of similar. One from Dimitri and one from Guillermo Rain, who are kind of asking about using this kind of coupled modelling and CFD with wind and fire. You mentioned yourself that there's kind of a lack of high quality experiments, and both of them are talking about the suitability of engineers using it with the level of validation currently available. Is it suitable? If so, how do people go about finding this kind of validation, stuff like that? I'll just publish the two questions to get the specific.
Yeah, there is a different way how we treat CFD in fire safety engineering and wind engineering. And wind engineers often say that simulation is wrong until proven. And in fire safety engineering, we tend to have this belief that our fire simulations are just correct because we've put some magical number into FDS and we received the correct answer. And I mean, I'm very careful about my simulations, and I treat them as a tool, not as a representation of reality. And if you treat it like this, I mean, you will probably not get a perfect representation of wind and fire in your setup. That if in reality you had this kind of wind and this kind of fire, I don't think the CFD would give you like the precise answer to that problem, but it still can be useful. And we need to have better understanding of what's happening and CFD is giving. So yeah, I'm aware that without large-scale validation of wind and fire, which is very difficult to obtain, and I would love to have that. I will work very hard to obtain that. Without that, we won't have a proof that it's the truth that the CFD is showing. But also, on the other hand, CV is computational wind engineering is putting a lot of effort to minimize the inaccuracy of CFD. There's a lot of wind tunnel testing to get the boundary conditions correct, to get the solution of wind-oriented CFD as close to reality as possible. And what we think that today, with the knowledge we have today, if we minimize the sources of error by using the best practices of wind engineering to have the best possible useful wind boundary condition and model, and we are careful about fire simulations with accordance to the fire engineering best practices, together this gives us the minimum uncertainty that we can have in the simulations. Is this representation of the true? No. But that's probably the closest thing we can get at the moment. And for the reasons I've mentioned at the start of my presentation, we need to do them regardless if it's perfect or not. And hopefully, as the future goes, as we progress our research, we will be able to improve that.
Yeah. Yeah, and it seems like you're on your way to try and work towards that a bit as well.
Yeah, it's the wind tunnel, man.
Yeah, that should be cool. There are quite a lot of questions, but there's quite a few on like specific specific setups and how people would need help and stuff. So I think if you do have interesting questions for Wojciech about this or for other topics, he's very active on Twitter at Wojciech ITB. It's a good way to contact him to find more specific information. So I think that's best for some of these remaining questions. Sorry if we didn't get to answer it. I will say, just at the end to sort of finish off, do you have, in terms of doing this research in the future, do you have any particular topics that you're interested in taking this forward? Sort of like just a window.
Yeah, definitely. We are starting with natural events and wind to identify the true performance of natural ventilators in wind scenarios at different settings. Also related to the way how these are placed on a rooftop. This is a very interesting. I saw on the feed the question if you can do a natural wind ventilation on a single facade if you don't have access to other facade. Yeah, so this research will also try to answer this type of question. And by the way, for now, I don't think you can do an efficient system like this. It's very troublesome. So yeah, the natural ventilators are the first thing we want to investigate. The second thing is the boundary between energy efficient buildings and fire, because if you want to have a LEED certified building or BREEAM certified building, you get a lot of points for your green score by having natural ventilation in your building. So because of this, we end up with skyscrapers that have natural ventilation at heights of 100, 200 meters above ground, very, very high. And there is no understanding on what will happen in fire for the safety systems of such a building if this building is a subject to a wind. And if the building is 200, 300 meters high, I can assure you it will be a subject to a wind when the fire happens, because this is how the atmosphere works. So it's very unlikely that there will be no wind. So there will be wind. And we have absolutely no idea what will happen when some of these openings are present. And the idea behind the green building is that the employees can open and close these openings as they like. So yeah, we don't know what will happen. Simple answer to that is you should put some mechanical mechanism that will close the windows. That's the easy answer to the problem, but that can cost literally millions. So it's $1 million question. What will happen, and do we need to close these vents? Yeah, so this is something that we are going to investigate. And the third thing is I'm absolutely fascinated by wind and fire phenomena. It's just I'm really fascinated by this, and I would like to help my fellow fire engineers, fire scientists, and try to define what kind of wind is important in fire experiments. Like, answer a question. I had wind of 4 meters per second, and I have performed an open plan burn in the field. Was this wind important for my experiment or not? There is no golden rules, no really easy way to figure that out, but I would like to investigate that and try to give some sort of simple general answer to the question. So if you try to burn a building and you know that your wind is 5 meters per second, you will know you will have a bad time, and it may be better to postpone the experiment or include that in your analysis. Yeah, so I think this would be very beneficial to the community of fire science to have this type of investigation.
Yeah, well, that sounds like you've got a lot of work ahead of you.
Oh, yeah.
And thank you again for taking your time out to give such an interesting talk for the SFP London student chapter. Thank you to all of you for listening on the other end. Before we go, I'd just like to say, if you do have any feedback on the talk or any topics you'd like us to cover, please, you can get in contact with us on Twitter. Follow us. We're at SFP London. The video of this talk will be made available on our YouTube channel. So you'll be able to find it there, along with previous talks and webinars we've given. I'm not 100% sure on the slides. I'll need to talk that over with Wojciech, but if he's happy.
Yeah, it's okay.
Okay, Wojciech's happy with that, so we can share the slides somewhere as well, probably on Twitter or on our website. Our website can also be found by Googling SFP London Student Chapter. That's where a lot of our stuff is. And yeah, I also want to bring up, we've got a competition running at the moment for student researchers or people who've recently graduated researching fire science. It's a video competition. We're asking you to do a 3-minute video talking about your research, and there's a chance to win £350 if you enter. So the deadline for that is 1st of October. So I highly recommend signing up to that if you are a student or someone who recently graduated from studying fire science. So yeah, thank you very much for coming, and we hope to see you at the next one. Thank you, Wojciech.
Thank you very much. Bye.
Bye.